Okay, so hello everyone. Thanks for tuning in. Welcome back to Physics Meets ML. We are very happy to have Uros Seljak as our speaker today. Uros is a professor of astronomy and physics at UC Berkeley. The physicist in the audience knows very well his seminal work in astrophysics and cosmology, but he is also very well known for his research in Bayesian statistical methods and more recently machine learning. He will tell us about normalizing flows for scientific applications. So take it away, Uros.
Yeah, thank you so much for the invitation. And before I forget, here's a list of my collaborations, and I particularly want to highlight my student B-Ray Dyke, who did a lot of this research on the normalizing flows. So here's the outline. What I want to talk first about normalizing flows in general, and then talk about one special case, which we call sliced normalizing flow. Then I'll talk about a couple of applications. One is anomaly detection and one is data analysis. And then I'll generalize or maybe constrain to more like convolutional normalizing flows. But in this specific case, with translation and rotation equivariance, which we are going to be applying to cosmology problems, which are kind of an ideal environment for this kind of symmetry implications. And then I'll talk about future directions and so on. Okay, so first of all, what are normalizing flows? They are mappings from a simple distribution to a complicated distribution, where each step of the map is a simple operation. And but because it's a let's call it deep network, so it's a sequence of these maps, at the end we may get a very complicated distribution. For example, very often we start from the first variable, which we call latent variable, z, and its probability distribution may be something very simple, like a Gaussian with zero mean and unit variance. So this is the base distribution. And then through these flow operations, we may be able to map it to data, for example. We map it to a data space, let's call it X, which may be very complicated and may contain a lot of complicated correlations between the data variables.
May I ask you a dumb question? Since there are indeed problems that flow distributions to distributions continuously in time, when I first ran into this, I was a bit confused by the discrete steps and calling it a flow. Is this a historical thing? Is there a reason to call flow something that is not continuous? Is it a little confusing? And just tell us, a little history.
Yeah, no, I don't know. I mean, it is continuous in terms of variables, right? And so maybe that's
no, but
enough.
not time. Yeah. Okay. Thanks.
Not time. Yeah. There's no time concept here, anyways, right? Although, of course, you could make it a time. I'll have it on the next slide. Yeah, sure. They can be continuous, and then they become an OD. All right, but so for this purpose, what we care about is that these transformations are invertible. So we can sample from them, and we also want the Jacobian to be evaluated so that we can evaluate densities. So these are the two main aspects of normalizing flows which are interesting, and I'll explain how they're interesting from a scientific point of view. So in 1D, the situation is relatively simple. What we do is that suppose we have some data which is not distributed Gaussian. Suppose we have some normalizing flow mapping F. We map at the beginning, for example, the map still doesn't look like a Gaussian. Suppose we want to now train this flow map to a Gaussian, and it turns out we can do it with a single step. That particular map would look like this. It would be based on CDFs, cumulative distribution functions. It's easy to derive what it would look like in 1D. And the point is that you can, using this mapping, you can map to a Gaussian. How would you train this setup? For example, you could train on maximizing the log P, because we know Gaussian maximizes the entropy. And so this would be one way to train this objective. Basically, we'll be training on the parameters of this function F, but the training objective would be, for example, maximizing the entropy, or equivalent, basically minimizing the KL divergence between the target Gaussian and the map. So right. So what we want to do is we want to generalize these to high dimensions. This becomes a difficult problem because we want to be able to evaluate the Jacobian easily, and Jacobians in high dimensions. These are the determinants, right, of very high dimensional variables. So this is not an easy problem at all in general. And also these functions, as I said, we want them to be invertible, so we can map them in both directions. So how do we do this? There are many different ways to do this, which I will not discuss. You may have heard of masked autoregressive flows or spline neural flows, and some of them are continuous, as we just heard, for example, and then they become ordinary differential equations. There are also stochastic differential equation versions. All right, the one I'll be talking about briefly is the one we have developed and published in ICML this year, and the idea is that we use slices. So the idea behind this is the Radon transform. What is a Radon transform? Radon transform says that any high dimensional probability distribution or density can be expressed as an integral over the slices, over one-dimensional slices. But this integral is, of course, over this n-1 dimensional sphere of all possible slice directions. So the transform is actually very easy to write down. It's basically a generalized form of Fourier transform. And the only difference respect to the Fourier transform is that you have the wavelength, the wave vector to the power d-1, where d is a dimension. Okay, so you may have seen the results of this, at least in the CAT scan examples. For example, imagine you are trying to map a two-dimensional image of something, let's say a brain. You CAT scan the way it operates. It projects in all possible directions and measures the intensity of these projections or slices. So this is shown here. This is the input scenogram. Then what it does, it first Fourier transforms on each slice. So it does a Fourier transform of each one. Then it arranges this around the circle in this two-dimensional pattern. And then it does the inverse Fourier transform, and voila, you get an image of a brain. So this is a general theorem in any dimension. So we know we can represent any dimension, any high dimensional density with its slices. That is the theorem that we're going to rely on. Now, the problem is that as you go to high dimensions, you get hit by the curse of dimensionality. You can no longer do all possible directions like you are doing here in 2 dimensions. So curse of dimensionality is, I guess, in principle, an unsolved problem. And of course, we are all struggling with it. But there is one thing we can do, which let's call it the next best thing, which is, well, instead of looking for slices, instead of doing all possible slices, let's look for slices that are in some sense maximally different between the 2 distributions. All right, so here is the idea. So imagine you have, again, 2-dimensional problem. Your initial distribution is blue, your target distribution is orange. Now what you can do is you can look for directions, different slice directions, where the difference between these 2 is the largest. And so in this case, for example, we find that this direction is the largest. And how do we find this? Well, because we see that the PDF of blue is very different from the PDF of orange. How do we look for these directions? We use actually Wasserstein distances in this case. And so the distance is in some sense the best possible distance, well, in a well-defined sense, Wasserstein sense. This is an optimization problem, right? Because we optimize in all possible directions to find the largest possible deviation. So once we have found this deviation, then what we can do is we can match the 2 distributions along that slice, and this is shown here. And now what this does for the overall distribution is it brings blue closer to the orange. In this case, it does this. All right, so then what do you do? It's still not perfect. What do you do? Well, you look for a next direction, next slice direction. And in fact, you can do several directions at once by making them orthogonal to each other. And so this becomes an optimization problem in a Stiefel manifold. And this is still solvable. And so we're doing for k directions at once, where k usually for low dimensional problems is just the dimensionality of the data, and for high dimensional problems is some fixed number like, I don't know, 20. All right, so because we're doing this many, many times, this becomes a flow, a deep, a deep network. This certainly has a structure of neural networks because these slices are orthonormal projections, and so they are really just linear operations. These are just rotations, and the nonlinearity, this mapping is a nonlinearity, is a pointwise nonlinearity, but it's much more general than a typical ReLU nonlinearity, right? Because it's basically a mapping between these two distributions, which can be derived, and anyway, it's much more general. Okay, so that's the idea. How well does it work? Well, we can generate images with this. Here's an example of fashion MNIST, where we start from white noise, and after 20 of these slice iterations, we get this, and after a few hundred, we get a perfect image. We get similar results for celebrities. Here are some of the samples that we have obtained with this method using MNIST, fashion MNIST, CFAR10, and Celeb A. And in terms of these scores that people like to talk about, fit scores, this method is pretty competitive. So these are very high dimensional examples, right? So this is 800 to 3000 dimensions. So this method certainly can work in high dimensions. It can also interpolate between the data. So here's an example. If you want to interpolate between two initial and starting point, the interpolation along the way will also be an image with high density. In other words, an image of a reasonable, in this case, face. And the nearest real image in this case, for example, would not look anything like what we started from. So there's no collapse onto the training data, and interpolations work well. Okay, this is not the application I particularly care about, although I'll show examples in cosmology later. But what we care about perhaps more is the fact that if you train, you can train from the Gaussian distribution to a data, or you can train from the data to a Gaussian. But what comes out of this training is the likelihood, P of X, the density estimation, let's call it. All right, so now this method is not state of the art in terms of density estimations in if you have a lot of data. Here I'm showing the results compared to the standard methods. And usually the winning method these days is this NSF, neural spline flow, but they're all very similar except for KDE, which is much lower. They're all very similar in terms of log P, average log P at a large number of training data. But an interesting thing happens when you have small amounts of training data, let's say 100 to 1,000. In that case, our method actually systematically outperforms other methods. It's always the highest. These are examples from 6 dimensions to 63 dimensions. These are standard UCI examples. They are pretty ugly distributions, actually. So this method seems to have something in it, let's call it inductive bias, which is specifically well matched to this kind of data sets, so that it actually does very well for small training data, and it outperforms other methods. The other thing, in this method, we have very few hyperparameters. But there is one which we call regularization, and if we have high regularization, we get slightly better results than low regularization. But even with low regularization, which is the cyan numbers, results are pretty good. Now, the method is extremely fast, especially with low regularization. We're talking about seconds. This is the number, or the time it takes to get this result, the training time, not the evaluation time, but the training time. So we're talking about seconds, and many of other methods, we're talking more like minutes to even hours, right? And so this method is particularly fast, and which is going to be important for specific applications I have in mind later. Okay, so what can we do with this? One fun application is anomaly detection, and there was this competition, actually, a blind challenge that was organized by the first 3 authors of this paper. At the end of 2019 and beginning of 2020. So, and this was LHC Olympics. And the idea was to inject a lot of background, to simulate a lot of background events, and then inject some signal, which they didn't tell us anything about it, what it is. And you were supposed to figure everything out yourself. It was a completely unsupervised challenge. So now there were, since this was an LHC event with jets, we first ran a jet finder. We said, okay, we're going to go for jets. We're going to look for their their jet mass, the total mass of the combined mass of the event, which we're calling MJJ, and also we're going to be looking for subjettiness, in other words, how clumpy the jets are. So we decided to use these 4 variables plus the jet mass, so 5 variables. And so what we were doing was we were looking for density estimation as a function of this total mass, with the idea that if there is a resonance in there, then maybe this resonance will show up in a higher density at the resonance point in terms of these other 4 variables. So this was 4-dimensional density estimation, conditional on this mass M. So it's conditional 4-dimensional density estimation. And so what we were doing, actually, we were looking for contrast relative to the neighboring mass beams. So really, for example, you can see here there's a clump, and there's no density neighboring bins. And so, we will take the ratio of these two, and this is shown here. And if there's something injected there, then maybe there will be an excess. This plot here is actually from our submission. This is actually from last month's third courier. And basically, as they said, the best performance on the first black box was by a team of cosmologists at Berkeley, which I thought was kind of amusing. I'm very impressed by high energy physics experimental community in terms of their machine learning skills. They are far advanced compared to us cosmologists, if you ask me, right? So it was kind of fun. I thought that we beat them at their own game in this case. Here's an example, for example, of how we do. Here's the cross section. For example, we said there were 1,000 events injected, and indeed the correct answer, we were bang on. But everybody else actually predicted a lot more. In fact, some of them predicted a few 100,000 of these events, which I don't know. I don't even know how that's possible, given the total number of events is 1 million. Anyway, you get basically the idea that this thing can actually look for very, very small signals and identify them in a kind of unsupervised search. Okay, let's move on. The next application I want to talk about is something very close to my heart, which is Bayesian analysis. And this is still work in progress. I don't know if it will lead to anything, but it's been a lot of fun. So where do we need high-dimensional density, probability density distributions? In Bayesian posterior analysis. So uncertainty quantification with Bayesian posteriors. So what's the problem here? We want the posteriors, P of y given x. And y can be multidimensional. Y would be the parameters you're trying to estimate. But maybe there are also a whole bunch of other parameters that you don't actually care about, like nuisance parameters. In cosmology, for example, we always have to marginalize over a lot of things that we don't actually care about, but we need to marginalize. At the end of the day, we are interested in one-dimensional posterior, but usually the problem is actually in high dimensions, and because these variables are correlated and things like that. Okay, so the method of choice is MCMC, Monte Carlo Markov chain sampling, and there's a lot of different flavors of this: Metropolis Hastings, Hamiltonian, Langevin, Gibbs, nested sampling, sequential Monte Carlo. There's a lot of these flavors that I won't get into. But I'll just point out that, yes, this is the method of choice. It works, obviously. We're all using it, but we have a lot of problems with these methods. The chains are correlated. We need to thin them. Sometimes these correlation lengths are ridiculously large. In high dimensions, they can easily be tens of thousands, really. I mean, this is incredibly large correlation lengths. So second problem is burning. We have to first do the burning. It's very expensive. The acceptance rate might be very low in these chains, so on and so forth, right? So it's fair to say, at least in my field, that most of our CPU time, we get a lot of supercomputer CPU time. And what do we spend it on? Not on fancy supercomputer simulations, but on running MCMC chains, actually. So that's the reality. Okay, so let's look at this from the optimization view. The idea is, let's try to approximate this posterior with some approximate distribution Q of y, which we're going to fit with our method, synth method. Okay, that's the idea. Now, this is a harder problem. Why? Well, first of all, we don't have access to this posterior. We only have access to the joint distribution. In other words, joint distribution is the likelihood times the prior. This is P of x comma y. X is the data, y are the parameters. We do not know the normalization function, or the partition function, P of x, so we cannot write down the posterior explicitly. But more importantly, we just don't know where this posterior is going to peak. We don't know a priori this. So previously, we had samples from the data X, and we were able to fit the density to that. Now, we cannot fit directly because we don't know where the density actually even peaks. So this is a harder problem, and this is why this sampling problem is one of the most challenging problems, actually, for our, that is also very important because we want to get uncertainty quantification using Bayesian methods. Okay, so what is our basic idea? We're gonna try and get some approximate Q of Y, and then we're going to correct it by using importance weights. Importance weights basically just say that if you have some approximate Q, then you can, for any expectation of any function, let's call it Y to some power P, this will be expectation which we integral over the posterior, but instead of integral posterior, we replace it with an integral over Q, but applying these importance weights, which are P over Q, basically. That's the idea. So, here's an example of how we do this using a temperature annealing. So what we do is we go through several temperature levels from beta of 0, so high temperature, to beta of 1. And what we do is at every level, we fit a new SIMF normalizing flow to the existing samples. Okay, and then we reweight these samples by using importance weights, and we just keep doing this. So here's just an example in low dimensions. In 2 dimensions, we have a Gaussian mixture. At low beta, the red is our SIMF approximation, and I'm also showing blue here, which is actually the density of the samples themselves. It's useful to also know where you have the samples in this case. Anyway, red is the one you want to focus on, and at low beta, you get something like this. You perhaps sense there's an overdensity at the 2 Gaussians, Gaussian peaks, but you don't quite know that that's true. And then as you slowly increase beta to 1, then you completely zoom onto the 2 peaks, and you get the correct posterior. There's a related problem. And does it work for Bayesian posteriors in high dimensions? Well, that's of course the million-dollar question. We don't yet know, but we are having some preliminary results that are encouraging. Here is an example of 10-dimensional Gaussian. This is not an easy problem. If you have 10-dimensional Gaussian, which is correlated, and the correlations are pretty strong, as you can see. As I said, this is not easy, especially not easy if you don't have access to gradients. Now, I forgot to mention, a lot of these applications in cosmology are without gradients. We don't often know how to write a gradient of a model with respect to the parameters. I have a separate project talking about differentiable universe and differentiable this and that. I think we should move away from having non-differentiable simulators and going into the differentiable direction. But that's a challenge for the whole community to go that and do that step. Right now, we're not there. So right now, a lot of our codes do not have a gradient. So this example here is without using the gradient, because let's say we don't have it. And then it becomes a much harder problem, as I said. And so in this case, for example, we converge to a perfect posterior. So there are 2 lines here, actually. One is red and one is blue, and 2 contours. One is red, one is blue. They're pretty much identical. That's why you don't even see red. So we got a perfect result with about 3,000 sample calls. These were 10 beta levels. Each level we were calling 200 calls each, but sometimes we had to repeat. So maybe it was, let's say, 400, so it was about, as I said, 3,000 sample calls to get a perfect distribution. This is actually quite good. I think it may even beat whatever state of the art is, let's say Metropolis Hastings or sequential Monte Carlo. So this result is encouraging, but of course this needs to be tested on much more challenging problems, and we haven't done it yet. Now we did actually receive a very large grant actually from DOE Oscar to actually study this problem. So hopefully there will be more results coming, and hopefully the group will get larger, and this thing will become a real thing. I don't know. I'm optimistic about this, but we'll have to see. There's a related problem, which is global optimization, which is how do you find just peaks? So in this case, you don't look for the full posterior distribution, you just want to go for the peak. So here is this 6-hump camelback, one of the standard optimization problems. It has 2 peaks, which are the 2 stars. It's an ugly distribution. And in this case, for example, so we use the same strategy as the one I was telling you before, the annealing strategy, except that we don't do the full posterior sampling at each temperature level. We just do devise what we call acquisition function, which is very similar to the way Bayesian optimization works. In this case, the acquisition function uses information from our current estimate of the function, which is this red thing, and our current density of the samples, which is the blue thing. All right, so the idea of our acquisition function is to go for where the things are most promising, that's exploitation. These will be the peaks of red, but also go for things where we haven't sampled things well enough yet. So this would be exploration part. This is where the low density comes in. And we can do both the density of the samples and the density of our target with these normalizing flows. So we're using SINF for both of these things. And so here you see what happens when we go to the temperature levels. We slowly add more samples in the high density regions, but the density of samples is always trailing the estimation of the function. And we converge onto both of the peak section in this case. In this case, we needed 35 calls. So these things are very useful when your evaluation is very expensive. In cosmology, for example, we have a lot of examples where our likelihood evaluation is very expensive. Even just standard linear analysis will take seconds, which is a lot. If you need to run millions of samples, then this becomes a lot. But then if you go to embody simulation, stuff like that, then seconds may become days or weeks or who knows what, right? So, expensive likelihoods are certainly a thing, at least in our field. So let's see, there's another problem, which is double Gaussian, similar idea. And again, here we were using 40 calls to converge. In this case, this is a higher peak. There are 2 Gaussians. He explores both for a while, right? And then he decides, okay, I'm gonna just keep on doing on this one because this one is not interesting. And that's exactly what it does here when we go to higher beta numbers. So, all right, so this is competitive with the best global optimization algorithms, such as Bayesian optimization, genetic algorithms, and so on. So, right, so before I move on, I want to bring a couple of more physicsy ways of looking at what we're doing here. First is that we can view normalizing flows as preconditioners. In other words, they change the geometry of our target distribution. Suppose that the target distribution before was this joint distribution, P of X and Y, where Y is now mapped into latent space, but the mapping also incurs the Jacobian, right? So you can think of the target distribution, P of Z, in latent space as being the target distribution in original space times the let's say, inverse Jacobian. And so the goal of these normalizing flows is therefore to simplify the geometry in the latent space. Okay, and one way to think about it is it generalizes this idea of preconditioners that have been used for many decades, really, like let's say Newton's method, right? Mass matrix in Hamiltonian Monte Carlo, the mass matrix in Metropolis Hastings. These are always the ideas that if you precondition, you will converge faster on the sampling. And the normalizing flows are an extension, generalization of this idea to distributions which are not Gaussian. Maybe there's a banana, maybe it's multimodal, anything you want, really, this method can handle. So, so the procedure, so there's another procedure basically that one can therefore add in this latent space. One can just sample from this target distribution using standard Metropolis Hastings sampling. Even that will be accelerated. The acceptance will be accelerated because the geometry in this latent space is going to be very simple, very Gaussian. So, so acceptance will therefore be higher. So that's a different method from the one I was just showing you on previous slides, but it just says that, and this method, by the way, hasn't been tried yet. We are working on it. We'll see how far we can push it. But the idea here is that we have several venues how to improve the sampling rate, and acceptance rate. Okay, so now if you have gradients, then you can also do Hamiltonian enlangement sampling, and this has been actually done, and I'll show that on the next slide. Right, so let's see. I guess I lost that slide. Right, anyway, the bottom line is this precondition, this normalizing flows can simplify the geometry. Okay, before I move on, I just want to mention there's another extension of these normalizing flows. So far, I was talking about surrogating the probability densities. You can also amortize them. Amortizing means, so far, basically what I was doing, I was approximating or surrogating this posterior P of Y given X with Q of Y for one data realization X. But, so this would be, let's call it surrogating of the probability densities. Amortizing would say you are actually then also approximating this for everything that this is conditional on, everything behind this bar, right? Because this behind this bar doesn't have to be probability distribution, doesn't have to be normalized and so on, but there's still some functional dependence on these variables, in this case, the data X. So you can therefore amortize with respect to all possible, in this case, all possible data realizations X. So, and if you do that, then you would basically run many data realizations X and to train this thing. And so this will be then conditional normalizing flow. And this parameterization with respect to X is usually done with standard neural network architectures, okay? Pre-training is more expensive because you're doing it for all the data, but the posterior analysis itself can be done faster. So there's an interesting interplay here. When do you do this, what I just described, and when do you switch to this amortizing part as well, where you pay the price in pre-training, but then later it's cheaper. The answer, an obvious answer is whenever you have to do the same analysis many times. And we have lots of examples like that, right? High-energy physics experiments, they just keep observing the same detector over and over again. Exoplanets, for example, microlensing, strong lensing, gravity wave analysis. All of these are examples where you, in some sense, you're repeating the same analysis and where amortizing makes sense. In fact, for example, there's an interesting example, not from my work, but from this Dax et al., where they apply these to gravity wave, LIGO, and basically they're showing here, this is a like 10 to 15 dimensional example. And here, one is a true posterior, the other one is their amortized posterior using normalizing flows. And the posteriors are not simple. For example, here's the localization, very, very non-Gaussian bananas, right? But they get pretty much a perfect agreement in this case. So this is another direction where normalizing flows, I believe, are going to be extremely useful for the scientific applications. And we really see examples like that. This is a particularly interesting example because this particular community it has been using nested sampling, which I think is extremely slow sampler, and so they've been frustrated by how slow their results were, and these normalizing flows are just going to blow away, I think, any kind of nested sampling applications. Anyway, that's my prediction and my expectation, and I'm certainly interested in pursuing this further myself. Okay, so let me move on now to cosmological data analysis. Now, what do we want in cosmological data analysis? We want to model the data likelihood or the posterior. Again, we have some data X and we have some cosmological parameters Y. Now, even in the Gaussian case, even if the probability, even if the likelihood is Gaussian, we can write it down analytically, but it's not easy to solve this because we have a survey mask, and we have noise, and we have to invert these covariance matrices, and this becomes an n-cubed problem where n is the number of the data, and this n can easily be millions, and this becomes actually an unsolvable problem. So there are approximations that need to be done even in the Gaussian case where we know how to write down the likelihood. In the case of non-Gaussian situation, we don't even know how to write down the likelihood, we don't maybe even know how to write down the noise model in some cases, like what is the noise of a galaxy, and so on. So there are a lot of issues that we don't know how to do. So what is the standard thing to do is that we form summary statistics, let's call them capital S. Maybe this is a power spectrum. Now, you think power spectrum is the information. Yes, it is, but the way you form it in a nonlinear case, for example, it's still a power spectrum, even though it's nonlinear and doesn't contain all the information. So what do? Well, you supplement it with something else, maybe 3-point function, or maybe some other statistics, voids, peaks. There's so many of these statistics that people have come up with in cosmology. So these are summary statistics. First, you need to construct basically their probability distribution. Maybe you can model them as a Gaussian distribution, in which case you need the covariance matrix. And then you build this implicit likelihood, right? So that's a standard approach, the way we are doing it in cosmology. It's very expensive, and there's no guarantee it's going to be perfect. In other words, there is information loss because we have used some summary statistics that we don't know how much we lost. Now, there is a way to do optimal cosmological analysis, which is to write down the likelihood and have these nonlinear operators, the forward model operators in there. For example, here's an example of a likelihood like this. This is the likelihood of a lensing effect on CMB. So we have some CMB field, let's call it F, which it comes with its own power spectrum. And we know it's Gaussian distributed. We have some lensing field phi, which here we assume it's Gaussian and it comes with its own power spectrum. But then we have this lensing effect, which is a nonlinear operation. And it takes the lensing field phi and it does something nonlinear to it and maps it on the CMB, and that's how you compare to the data. So this seems easy, but this is a very, very high dimensional problem. And what is a function of this, so we can write down the likelihood. If you know the detector noise and so on, we can write down the likelihood, but this is a likelihood, implicit likelihood in terms of these latent variables, in this case, CMB field and phi field. What we care about in the end is perhaps just cosmological parameters that are hidden inside these power spectra. So we need to marginalize over these latent space, and that's a high dimensional integral, and that's the source of the problem. Okay, so this is why these things are not easy to do. What we have asked ourselves is, can we learn directly the likelihood without using this implicit likelihood as a function of latent variables? If we can do this, there will be no summary statistics, no information loss. That would be great. But the difficulty is that this is a very high dimensional data space. So just doing, naive amortizing, as I was describing earlier, would not work. So what we do is we develop, we will go in with normalizing flows for the data, actually, in this case, conditional on the cosmological parameters. And then the question is this even possible? Because the dimensionality of data can easily be millions or even billions in some cases. Okay, so let me describe now this translation rotational equivariant normalizing flow. The idea is, let's take, for translation invariance, let's take convolutional idea. Let's work with convolutions, but let's put that into a normalizing flow framework, and let's enforce also rotational symmetry. Okay, so how do we do this? First of all, we do convolutions in Fourier space. We do everything in Fourier space because we know the convolutions in Fourier space become just a product. And then in that case, all we need to do is we need to learn what we call these transfer functions that multiply the data with. But the second thing we do is, because we know we have rotational invariance in cosmology, we make these transfer functions only functions of the wave vector length, not the direction. Okay, so this is a vector, this is now a scalar here. All right, so this is how we enforce rotational symmetry. It's not the only way to do this, but it does do the job in terms of enforcing the rotational symmetry. Okay, and this then becomes training on this one-dimensional function that we need to do. Okay, and then the other thing we do is, after we have trained, then we do exactly the same thing as what we were doing in SIMF. We look for one-point distribution function along that, let's call it generalized slice, and we look at how non-Gaussian it is. We look for direction of maximum non-Gaussianity, and then we map that to a Gaussian distribution. And we keep track of the Jacobian and keep track of the mapping, okay? And so this becomes then a normalizing flow. We typically use a few layers only, let's say 5, where we train this transfer function parameters T of K, and we train this 1D distribution, 1D probability distribution mapping, which is the same as what we're doing in SIMF. All right, so the number of parameters is actually relatively small, of order 100 to 1,000. And that's good because it means it's faster training and less overfitting. It certainly has normalizing flow structure, which is good because at the end of the day, we will use these likelihood evaluations. So now, as I said, this is just the likelihood of the data, but we won't do this conditional on the cosmological parameters because we want to do cosmological inference in the end. So that's then amortizing part, right? And we, again, do that with the standard neural networks where we just interpolate basically the different cosmological parameter values. All right, so let me show the results. Is there a question? Sorry, I can't see the question. Okay, let me wait for the end. Okay, let me show the results here. Here's some experiments. This is on a projected n-body simulation. So we're doing this on 2D projections. We vary cosmological parameters, in this case, matter density and amplitude of fluctuation, sigma 8. And we model this with a 5-layer TREMF architecture. Let me just show the results on the samples. As I said, normalizing flows are nice because you can both draw samples and get the likelihood. So, and these are the 2 main tasks. So here the samples would be literally, you can think of this as new n-body simulations. Here's the training data I'm showing. This is what went into the training. And here we're varying omega matter in this direction. So you can see that as omega matter goes down, we get more larger voids. Okay, this is well known because the power spectrum gets redder in this case. And then in this direction, we're varying the amplitude of fluctuations. This is low amplitude, this is high amplitude. You can see that for high amplitude, we get more clustering. Okay, visually, this is what we get. Sorry, this is the training data, and this is what we get on the samples. And visually, they're indistinguishable. All right, so we get pretty much the same structures, same looking structures on the samples. The same is true if you look at any statistics we have looked at. The power spectrum is identical. Sorry, this is the power spectrum. The 1-point distribution function is identical. The power spectrum is identical. The 3-point function is identical. So on all the statistics we looked at, we get identical results. In fact, that's true also in the opposite direction. What normalizing flow does, it maps from the data to the latent space. We know, and the target latent space is a Gaussian. So you can look how well it does also in the latent space. And again, all the summary statistics show that there is no deviation from a Gaussian. But you can do more. You can also use your neural network in your brain, in your eyes, to look for any deviations from Gaussianity. Here, for example, we have mapped this thing to the latent space. This is the result. And by eye, I don't see any evidence of any deviation from Gaussianity in this map. It looks like, you know, multivariate Gaussian, uncorrelated Gaussian, white noise, basically. But if we had used the wrong cosmology on this, then we would have obtained this result. And you know, here by eye, we see, well, there's some ringings, which are consequence of these transfer function effects. And you know, things are clearly non-Gaussian in this case, right? So this is also telling us that there's something wrong. And so this is nice because we can use this latent space maps to verify if we have achieved our target goal. If we have not, then maybe we're missing some systematics in the data. Maybe we're missing some effects, like baryonic effects, things like that. We can verify a lot of things by looking at the results in the latent space. Or maybe we're missing some real thing. For example, maybe this kind of ring would be a signature of some real some real non-Gaussianity in the data. That would be super cool, obviously. And so the point I'm trying to make here is it's actually much easier to look for, let's say, primordial non-Gaussianity in this latent space than it is in the original space, because the latent space is supposed to be Gaussian, and therefore it's easy to look for 3-point functions or whatever you want to look in terms of non-Gaussianity. All right, so, what is, to me, the most exciting part is the posterior analysis. Because this method gives us the likelihood as a function of cosmological parameters, then it's actually very easy to invert this by the Bayes theorem and get the posterior of cosmological parameters given the data, right? That's just the Bayes theorem. And if the prior is flat, P of y is flat, then really that's just the likelihood, you know, properly normalized likelihood. So what I'm showing here in red is the results if you just use the power spectrum information, which is a standard thing to do. And then in green, we show our results when we use our training of the full likelihood. And we have improved the errors in terms of figure of merit by a factor of 6. In other words, the area, the green area is 6 times smaller than the red area. So we have enormously increased the amount of information in this case. But what I'm more excited about even is that the fact that we actually get the correct answer, in the sense that the green contours are typically, so the stars, which is the true answer, are typically within the green contours. That's very important to verify, right? Because sometimes you may get some results, but they may not be reproducible in terms of the errors, right? The error might be under predicted. This actually is a standard problem of machine learning. The errors are usually unreliable in machine learning. Here we actually are getting reliable errors, which I think is a big thing, and it's something that in scientific community something we need to focus more and make sure that these machine learning methods are also getting correct errors, not just best possible classification or regression. All right, so do we recover correct information in the situations where we know the answer? Here's the Gaussian case, which as I said before, in that case, we do know the answer. And we basically get perfect results in this case, both in terms of cosmological parameters and in terms of the likelihoods. So it certainly recovers correct answer in the cases where we can verify. And then it's also very easy to add the noise. So here we added noise to this data. And what happens in this case is obviously the error contours get larger because of the noise, but they're still, you know, very complicated bananas in this case, because there's a degeneracy between these two parameters, and it gets worse if you have more noise. And these contours, you know, are reproducing this degeneracy very well, right? So we get good results with adding noise. And in terms of adding noise, it's very easy. You just add noise to the training data and then train on that. So preliminary, the hard part is modeling the survey mask because it breaks this translation rotational equivariance. And so what we need to do is we need to add layers which break this. In this case, for example, we have added simply pointwise PDFs, which depend on each point. In fact, they depend on the distance from the mask to make it simpler. And so that's how we were training this particular example. Here we removed half of the data. And in terms of latent space, this is what we got. Okay, so it's maybe not as perfect as before. Maybe if you squint, you maybe see that there's some edge still effect there, but it looks reasonably Gaussian, let's say. So in terms of cosmological parameter analysis, this is what we get in this case. With the mask, we still get very good results. And what I think is particularly encouraging is that in terms of figure of merit, without mask, it was 1,000. Now with mask, it's half of that. That's good. We have removed half data. We expect to have half of the information, but not more than that. We haven't lost more than what we expect. So that's great. So I think the method is working very well, and it lost information as much as needed and not more. So I'm very pleased and encouraged that this is working very well. So future directions are basically, there's many different directions. One is we can make this TREMF an Eulerian n-body simulation. All we need to do is to define this latent space to be the initial conditions. So far, we haven't trained on that. This latent space that we talk about is something, we didn't bother to connect it to initial conditions, but it would be straightforward to have another training loss so that the latent space that we talk about is actually space of initial conditions in an n-body simulation. And in that case, then we can create an n-body simulation where we start from initial conditions and we just make time slice outputs, which would be built by TREMF. So this will be a grid-based n-body simulation, which so it wouldn't be n-body anymore, right? Because it would be grid-based. So that's an interesting direction to do. We could also, of course, do the same thing with velocities. So far, I've only been talking about the maps of the density, but we can also do the same thing with velocity. Then we want to generalize this to redshift space distortions and velocities. Now, redshift space distortions break the rotational equivariance. And so that's something that will be harder to do, and certainly we want to go there because a lot of our data, like DESI survey that just started, has redshift space distortions, so we need to incorporate velocities into this thing. And then we can also make TREMF an Eulerian hydrodynamic simulation. Now this is similar to something that I haven't talked about, but I'll show you a few slides on this. Where we use Lagrangian particle displacements. But here we want to do the same thing, but using Eulerian maps, which are basically grid-based, and they would also be invertible, and they would have a P of X. So that's our target. But let me just show you where we are on this Lagrangian idea. The idea is, well, let's train on some high-resolution hydrodynamic simulation. Take a crappy simulation like these fast PM simulations, low resolution fast thing, and then train it on some very super duper high resolution hydro, and get the best of both worlds, right? And so this is the result of this kind of training. This is for the dark matter. This is TNG, the super expensive hydro simulation. And this is what we achieved on using this training, using this Lagrangian training. And you can see that basically the results are by eye indistinguishable. And in fact, we can show that our simulation is better than the TNG simulation at the same resolution. That's because we have trained on a high resolution TNG. So, but moreover, what is more important, our simulations here are 1,000,000 times faster than original TNG simulations. But we don't need to train just on dark matter. This is a dark matter map. But we can also train on stellar maps. So for example, here's stellar map of TNG, and here's our LDL map. And again, they look very good by eye. Here is kinematic linearity dodge effect. They're pretty much indistinguishable by eye. And all the statistics also show the same thing. And here is, for example, thermal linearity dodge effect. And again, they look very good. Here, I'm always showing redshift 0, redshift 0.5, and redshift 1. And this is basically how well they compare. Okay, so yeah, these are the conclusions. I've talked about several different normalizing flows. In cosmology, particular excitement about this approach is that it may enable an optimal posterior analysis. So not only we can do this analysis, but we can also have some guarantees that this analysis is optimal. Why? That's because we have trained on the target, which is the smallest possible error. We can actually train on the target on the posterior, for example. We can use discriminative training on the posterior, and by doing so, we have been training on getting the smallest possible error, and by doing so, therefore, we have some guarantee that this analysis is going to be optimal. Okay, so that's one of the nice guarantees. Of course, it's only optimal within the constraints of your architecture. Maybe you're still underfitting. Maybe you need a richer architecture, but within the constraints of your architecture, this analysis can lead to an optimal analysis. And so far, we seem to be getting results which are optimal, and on the things we can verify, certainly are optimal. Now, in terms of future directions, we need to make this more realistic, including astrophysics like baryonic effects, cosmological observables like hydro observables, redshift space, mask, so on. Okay, a lot of challenges here. And I really want to conclude by saying, oops, it's not easy. This machine learning for cosmology is not easy. And in fact, if you look out, at least in cosmology applications, there are very few success stories so far. So there's no guarantee that this is going to work either, or the TREF will be optimal. But so far, this has been fun, and I think perhaps it is promising enough to warrant further explorations. So, and with that, I'll stop here and take some questions. Thank you.
Hi.
May I? Do we ask on chat or do we ask?
Please go ahead.
I wanted to ask something on your plans for the trends a couple of slides ago.
Yeah.
Thank you for the talk. It was fun. So in the future directions, you said something about make trends and Eulerian hydrosimulation. But do you mean make it a flow in time? I'm the guy who asked you about flow in time at the beginning.
No, exactly. Yeah, exactly. Make it a flow in time. So here I have results of one particular time, right? What I can do is just to give a simplified version of the idea. I can start from latent space, which is actually initial conditions in an n-body simulation. It turns out initial condition of n-body simulation is also drawn from a Gaussian with unit variance, right? And zero.
And if it was not, you could transform it to it. But okay.
Yeah, right. And so then, the idea is let's make this kind of maps as a function of time, right?
Okay.
Right. So that's exactly what you said, right? And so maybe we can just keep adding more and more these trend layers and just transform previous output to the next output.
Right? Okay. Thanks.
All right. So any other questions for Uros? There are a couple of questions in the chat box. Maybe we can get to that.
Yeah, so let me read them. So what do you think are the current dimension limits for these methods with respect to uncertainty quantification? You have TD here, but density estimation went up for 63D. Right. Well, I think it's a good question that I don't know the answer to. But just in general, what I will say is if you do not use gradients, then I believe high dimensional applications are hopeless. Because the posterior might be in some tiny corner in terms of posterior volume. In terms of ratio, posterior volume to prior volume, these numbers can be enormous. And so gradient free methods are just going to struggle. We know this from experience with other methods. I don't think this is going to be very different here. But when you start using the gradient of your objective, and use that information, then normalizing flows can still be very helpful because you can go into normalizing flow latent space and take advantage of the geometry of the distribution, let's say at the current annealing temperature level, and then sample much faster. And this is exactly what these people. Let's see. I have a backup slide. It'll take a while. Well, I'll need to find it. Oh yeah, this is a slide, for example, from this Hoffman et al., where they apply this idea of normalizing flows and combine it with Hamiltonian Monte Carlo, and then they show in that case that basically in this latent space, the Hamiltonian flow is much faster because it doesn't spend much time on the outskirts than it is in original space. For example, here they have 50 steps for the Hamiltonian flow and 200 steps for the original flow. So there's hope that these normalizing flow ideas will be useful even for standard sampling. Now, of course, I'm optimistic that maybe with gradients we can also get better surrogate model, and that's all we need to do. I'm hopeful, but I don't know, and we haven't even tried it yet to see high dimensions. So anyway, the bottom line is it's unclear how high in dimensionality we go, but I'm optimistic that we have enough strategies to explore that something good will come out of it. Okay.
Maybe we could alternate between the questions in chat and the questions from people in the audience. There's a question from Roberto. Maybe you could unmute yourself and ask.
Yeah, thanks. Hi, Uros. Really cool talk. Thanks. I wanted to ask you, importance weighting resampling is very noisy, especially in high dimension. It usually doesn't work. The reason why it works in your case is that because SINF is a good approximation to the target, or is there any other insight why it actually works so well?
Yes, I think SINF is a universal approximator, and B, I was kind of trying to argue that it seems to have, for small number of training data, it seems to be particularly good compared to other normalizing flows. And so I think, on this particular example that I've shown, the 10-dimensional example, this was 200 samples. We were training only 200 samples. So it's definitely low number sample regime where SINF does seem to do a very good job. By the way, our acceptance rate is in this 10-dimensional example is 20 to 50%. We now have a 30-dimensional multivariate Gaussian example. We need 30 temperature levels instead of 10, and we need 600 samples instead of 200, but we get a perfect answer with in 30 dimensions. Okay, so we are able to get very high acceptance rates in 30 dimensions.
And that extends to the tails of the distribution, because you show like
that's a big question. So yes, the first try it hasn't, right? And that's where we are right now. Yeah, absolutely, right. That's a big question, right? How well will you do on non-Gaussian distributions, on bananas and stuff like that? It's fun. Okay. That's our next thing we're doing. Yeah.
Thank you.
So maybe you can go back to the chat questions.
Yeah. So Brianna is asking, why do you get ringing when you use incorrect cosmology? This, I think, is an artifact of, artifact. These transfer functions, let's see, let me go back. These transfer functions are not unique. Okay, so this is this ringing question, right? Why do we get ringing? When do you get ringing? You get ringing when your transfer functions are sharp in K-space. And so that's a signature that these transfer functions are sharp in K-space. Now, we have not explored much regularization. Right now, all we're doing is the transfer functions we're fitting to a spline, which has 128 nodes. So we allow very, very flexible and in some sense, ugly transfer functions. We're allowing for that. Why? Well, because we have found that with fewer nodes, we get worse results. But could we have, more nodes and add regularization so that we wouldn't have ringing? My guess is yes, but I don't know. So I don't think we should focus on this ringing particularly because I think, you can get identical results probably by regularizing better and therefore not have any ringing. All right. There's another question on the chat. Should I go and cover that one?
Yeah.
All right. Do you have a reference for your results on globalization? Sorry, I forgot to mention everything I was talking about. Nothing is out. Sorry. This, I always like to talk about the thing is on my mind right now. If I have written it up like next month, it's already past history. I'm not interested anymore. So yeah, my talk. None of these things is actually out. So nothing is written up yet. So Hopefully, will be written up.
So, any other questions? So, do you have any thoughts on how to distinguish different shapes of non-Gaussian?
Different shapes of non-Gaussianity, you mean? Sorry, can you repeat the question?
Can you distinguish between different types of non-Gaussianity, different shapes?
Yeah. So, right. So my argument there was, okay, first of all, I forgot to answer, why do I want these to become Eulerian N-body simulation? Why do I want this latent space to become initial conditions? The reason is precisely to look for primordial non-Gaussianity. So in other words, to have correct spatial structure in these latent space variables. So that, just think about these latent space variables as, let's say, Fourier modes. This is what I want, right? I want these Fourier modes. Each latent space variable, I want it to correspond to a particular Fourier mode, in other words, to a particular spatial wavelength. Okay, so once I have that, right, which we have not done yet, but I think it should be relatively straightforward for us to do, then I can look for primordial non-Gaussianity in the latent space. So I have removed all of the non-Gaussianity that is due to the nonlinear evolution of gravity, or maybe nonlinear stuff in the galaxy formation. You know, I've removed all of that, and I'm left with primordial latent space. And so then it's much easier to look for primordial non-Gaussianity. And I can look for all possible shapes that people are interested in, right? I can look for local non-Gaussianity, I can look for equilateral non-Gaussianity. I can look for anything that people are talking about in terms of inflationary models and stuff like that. And it's going to be much cleaner to look in that space rather than in original data space. That's the argument here. And that's why we want to make this extra step to connect latent space to the initial conditions in a simulation, so that we can actually take advantage of the spatial structure of these latent space variables and really look for these equilateral combinations that people talk about in terms of their scales, you know, and stuff like that. Right?
It would be very cool if you could look for oscillatory shapes, which are very difficult to find using templates or any traditional method.
Yeah.
So let's see if other questions or not. There's a raised hand.
There's a Richard Feder has a question.
Yeah, hi. Really great talk. I really enjoyed it. I was curious, like along these lines with applications to field-based inference, whether or not, like, I guess, like what's the limit on like how like expressive your priors can be in this latent space? Because like I've seen some applications where like you make the prior like a Gaussian random field, and that like aids in the training in some ways in the high dimensions. But for some of these applications you're discussing, I don't know how appropriate that would be.
Sorry. But what exactly is the question? I have a lot to say, but I just want to make sure that I understand the question.
I guess like does assuming like a more expressive prior on the latent space, like a Gaussian random field, like affect your interpretation when it comes to like detecting like non-Gaussianities and things like that?
Yeah. Well, okay, I would say a Gaussian random field is not an expressive prior, right? I would say we take care of a Gaussian random field on the first layer without this nonlinearity even, okay? Or maybe just rescaling, okay, by the various rescaling, right? So, your question is a very good one in the following sense. This machine learning is always, in some sense, a trade-off between having very expressible architectures. In other words, you want your architecture to be universal approximator. At the same time, you want the implicit prior, right, implicit bias, as they say, to match the distributions which occur commonly in the applications you care about, right? And so from this perspective, I think our both SIMF and TREMF are good, because on the first layer, they do a Gaussian. SIMF does a multivariate Gaussian without any structure, so you can think of it as a principal component analysis, whereas TREMF does Gaussian with a translation notation and covariance, which you can think of it as a power spectrum analysis. Okay, so we do that on the first layer, but then we add more layers to see if there's more. All right, but those additional layers we can also penalize by saying, okay, let's not, let's put regularization there. Let's not do more. Let's not try to overfit, right? And so we have this ability to have both a good inductive bias for the problems we care about, and be a universal approximator, right? We are universal approximator. We can fit any function you want, but you need to pay more and more if you go to more complicated functions.
I see. Yeah, really interesting. I'm interested to see where this leads. So thanks.
Thanks.
So there is a question from Michael Churchill.
Hey, nice talk. I had just a larger question, I guess. You made some interesting points comparing normalizing flows to preconditioners. I wonder at what level it's possible to use normalizing flows as a substitute for preconditioners in traditional simulations. Have you thought about that at all?
Well, certainly there's a lot of work along those lines. People at Google, let's see, what's his name? Foyer, I think. No, Hoyer, I think. I forget.
Hoyer, Stefan Hoyer.
Stefan Hoyer, yeah, right. I think he did something along those lines. I don't know if it was normalizing flows, but certainly
it was more traditional, yeah, neural networks.
Neural networks, exactly, right? Yeah, yeah. So right. I don't have an obvious reference in mind right now, but it is a good question. Yes, whether normalizing flows have some additional quality there. Yeah, one should look at it. And as I said before, normalizing flows themselves can be seen as an ODE, right? And so that's another connection there that is worth exploring, right?
So I don't see any more questions. So maybe we could just wrap up here. So let's thank Uros for the excellent talk.
Thank you.